Let's describe the continuity of this function. We have to recall that a function is continuous throughout its domain. So for the domain, you use an interval to describe the domain, right? That means within that interval, you pick any x value and then you plug it into the function. The function is always defined. So the first problem, we have a graph. So we don't need any y value, just use the x. So the function is continuous from -7 to -3, right? So from this point and then all the way to -3. So this is from -7 and then all the way to -3. So since -7 we have a solid circle, then we use a square bracket. -3 does not have a solid circle, then we use a parenthesis. How about this dot? So we don't need to worry about it, right? So and then from -3 all the way to 4. What happens when x is equals to -3? When x is equals to -3, y is equals to this value. Because -3, that is x, right? Then the y is this value. This is a solid circle. When x is equals to -3, y doesn't equal to this, and y doesn't equal to this. So when x is equals to -3, y is equals to this. So if this y value, this mark is 5, then f of -3 is equals to 5 if this mark is 5. Move on. And then from -3 to past the 4, and then we use a solid circle, and then we don't need to worry about this. So when x is equals to 4, y is equals to this. So if this mark is 4, then when x is equals to 4, y is equals to 4. Not this point, not this point, because they are open circle. And then we start at 4, and then all the way to 6, right? So we start at 4, and then we go all the way to 6. So 6 is a vertical asymptote. Then we use an parenthesis. And then from 6 all the way to past infinity. So the function is continuous within this interval. So that means you pick any interval. So for example, you pick this one, and then you pick a value between -3 and -7. So let's say x is equals to -5, and then f of -5 is defined. That's what the continuity means. You pick a value within the domain, and then that number, plug it into the function is defined. So how about the blue function, 2x plus 1 divided by x squared plus x minus 2? So first of all, let's factor the denominator to see if there are any removable discontinuity. So f of x, the top is 2x plus 1, and then the bottom, you can factor that to x plus 2 times x minus 1. And then the top, you can factor out. There is nothing to factor out on top. Yeah. We start right there. So x plus 2, x plus 1, that creates 2 discontinuities. So x cannot be equal to -2, and x cannot be equal to 1. Are they removable? Can we cancel them? The answer is no. So that means they are non-removable discontinuity. What is non-removable discontinuity look like on a graph? They are x equals to -2 and x equals to 1. They are vertical asymptotes. Okay, so what is the domain? The domain is, so you draw a line, and then you punch a hole at -2, you punch a hole at 1. So not equal to this, not equal to this. So x can be equal to anything else except these two numbers. So everything between them, everything greater than 1 and everything less than -2. So the domain is -infinity to -2, and then from -2 to 1, and then from 1 to past infinity, we say that the function is continuous within this interval from -infinity to -2, from -2 to 1, from 1 to infinity, because they are the domain of the function. They are the domain, then the function is continuous within its domain. And then for the next function, we have a piecewise function. So for piecewise function, the best way to check it is, to check the one is using the left limit and the right limit. So for the left limit, we have a limit as x approaches to 1 from the left. That means we are taking a number that is a little bit less than 1. That means x must be less than 1. So the function that we are taking is the first piece, x. So you plug in a 1, then you get a 1, right? And then what about the next one? The next one is limit as x approaches to 1 from the right. So a little bit greater than 1, then we take the 2x minus 1. So this one is 2 times 1 minus 1. That is equals to 1. So since they are equal, our conclusion is limit as x approaches to 1 from either side of g of x, that is equals to 1. And then what happened when g is equals to 1? When g is equals to 1, so we are taking the piece where the subdomain is x greater than or equal to 1, which is the second piece. So we have 2 times 1 minus 1, that is equals to 1. That means we also have a solid circle at 1 comma 1. Okay, so at 1 comma 1, we have a solid circle, right? Let's sketch the graph really quick. So at 1 comma 1, so 1 comma 1, we have a solid circle. When x is less than 1, we have a line, right? Just x. Okay, so we have a line that looks like this. And then when x is greater than 1, we have a 2x plus 1, which is a little bit steeper. So we have that. So this line is steeper, 2x plus 1. And then this is x, and then they join at 1 comma 1. So that means the function is continuous at 1 comma 1. And then what about the continuity? The continuity is from negative infinity to positive infinity. So if you look at the y equals to x, you can plug in any number you want. You take a look at the 2x plus 1, you can plug in any number you want. What about their connection? Their connection is at 1 comma 1. Of course, you can let x be equals to 1. So that means for this piecewise function, you can plug in any value you want. But if you are picking up anything less than 1, you are using the first piece. If you are picking anything greater than 1, you are using the second piece. If you want x be equals to 1 exactly, you are using the 2x plus 1 as well, because if you look at the subdomain, the second piece, x is less than or equal to 1. So when x is equal to 1 exactly, you are picking the second piece. Alright, so that's how you describe the continuity. Basically, all you have to do is you find the domain, you describe the domain, and that is where the function continuous. Okay, so that's the end of this video. If you think the instruction is helpful, give me a like, share the video for me, let more people watch this video. I appreciate for your help and support. I will catch you all in the next one. Signing off for now.